Let's talk about representing curvilinear motion with coordinate system. Let's go with rectangular components. We're going to have two other ways of representing this, which we'll do in later chapters. But now we're just going to start with rectangular components. So let's say I have a rectangular coordinate system, XYZ, such fashion, and I have a particle moving on some path in space here. I can string up a position vector to that. Let's call it R, and R then will have an X component, a Y component, and a Z component. And each of these components will be functions of time. More specifically, scalar functions of time. With this sort of setup, we can figure out a magnitude of our position as x squared plus y squared plus z squared, the square root of that. And we can figure out a unit vector associated with that, which will be the vector, the position vector r divided by its magnitude. So this will give us a magnitude and a direction of that vector if we need it. And this is how we'll define our position in rectangular coordinates. So we have our position along our path. Let's find our velocity. So our velocity is going to be equal to the dr dt. So this equals the derivative with respect to time of xi plus d dt of yj plus d dt of zk. Don't know why I'm in yellow here. Let's go back to white. But notice that if we just look at one component, for example, this guy here, the derivative with respect to t of xi equals what? It equals the derivative of x with respect to ti plus, using the product rule, x times the derivative of I with respect to t. But since we have a fixed reference frame, I doesn't change as a function of time. So this is 0. So we're left with just dx dt times the position vector I, or the unit vector I. So v just equals dx dti plus dy dtj plus dz dtk. We call this velocity in the x direction plus velocity in the y direction plus velocity in the z direction. Or maybe we'll write it as x dot I plus y dot j plus z dot k. I think that's Newton notation. Again, here we can define a magnitude, which is the square root of x dot squared plus y dot squared plus z dot squared, or whichever coefficient you want to take and square in there, however you want to write that. And then we have a unit vector of the magnitude of v, or v over the magnitude of v. So it's in the direction of v over the magnitude of v. And this is always tangent to the path, as we showed before, tangent to path. Now acceleration is going to point in general towards the concave side of the curve, and our acceleration is dv dt equals some axi plus ayj plus azk, which is v of x dot I plus v of y dot j plus v of z dot k, or x double dot I plus y double dot j plus z double dot k. And the magnitude of our acceleration is the square root of x double dot squared plus y double dot squared plus z double dot squared. A over the magnitude of A for our unit vector, and that's where we sit. So let's do this. Plane is rising with constant velocity 10 meters per second. Let's find the magnitude of the velocity and acceleration at y equals 100 meters. All right, so the velocity in the y direction is dy dt. Now notice this is a curve of y versus x, not y versus t. But let's take this derivative of this function and see what we get. 0.001 x squared. Now notice x is also a function of t, so I'll have to keep that into consideration. But this equals 0.002 x. But then we have to do the chain rule times the derivative of the inside, which is the x, so times dx dt. So the derivative of the outside times the derivative of the inside. And this is the same thing as saying 0.002 times x times the velocity in the x direction. And well, that doesn't help us too much. Well, I mean, it ultimately will, but we've got this x and this v of x that we have to figure out before we can figure out even what v of y is. But here we could figure out x based on the y value that we're looking at of 100 meters. So let's do that. And so we have this equation from the plot, and we can solve for x. And when we do that, x turns out to be 316.3 meters. And that's when y equals 100. X is this distance here of 316.3 meters. So we'll just put that x there. Now we do have another piece of information here. It tells us that Vy equals 10 meters per second. So we have a relationship for Vy here now, And we say that this equals 10 meters per second when y is 100 meters, and when y is 100 meters, x is 316. So we can do some algebra here. Stick x in for this, 316.3, and now we can solve for Vx. So if you solve for Vx, you get Vx equals 15.81 meters per second. And that's Vx at this when we get to this altitude. Who knows how much time that is? So we have Vx, we have Vy. The magnitude of V is the square root of Vy squared plus Vx squared equals the square root of Vy is given as 10 and then 15.81 squared for Vx, and this results in 18.7 meters per second equals the magnitude of V. So that's our velocity. So let's try to do our acceleration in this confusing problem here. So we have this relationship up here for Vy, and we could take a derivative of that which essentially is going to be the derivative of 0.002 x times v of x. It's going to result in a product rule, to say the least, equals, so let's pull a constant out, of, let's see here, so this will be now an x dot times Vx, which is x dot times x dot. Product rule working here. And then our second idea is going to be x times, well, essentially x double dot, because Vx is x dot, or Vx dot. I guess we'll use the same symbols that we're using here. V dots of x. So now we have some values that we can stick in here. So d dt, and this is at 100 meters, I guess. So at y equals 100 meters, then this is 10 meters per second and 0.002. We've got the velocity in the x direction squared, which we calculated up above. Put this in different colors, is 18.7 squared. And then we add to that the position of x that we calculated above as 316.3 meters. And this is multiplied by v dot x is the acceleration in x. Yeah. So therefore, acceleration in the x equals minus 0.791 meters per second squared, and I can calculate the magnitude as this quantity, and that equals essentially just 700 or 7.91 meters per second squared. And that's our value for the magnitude A.